Hello, Internet, and welcome to Film Theory. Today we're going to be talking about the classic, award-winning film, Interstellar. Specifically, we're going to ask whether the time dilation on Miller's planet is accurate to how time dilation works in real life. To answer this question, we're going to need a lot of math, so let's get into it. First off, we're going to compare the sun's gravity to the Earth's, because the sun's gravity is equivalent to one solar mass. The way we measure black holes is using solar masses. So to compare Earth with a black hole, we will have to scale it with the sun first. First, gravitational acceleration is 9.8 meters per second squared on Earth. And the sun has a gravitational acceleration of 273.42 meters per second squared. So the sun's gravity comes out to be around 27.8 times stronger than Earth's. The movie tells us that Gargantua, the black hole from Interstellar, is 100 million solar masses. So we'll take the sun's gravitational acceleration, which is 273.42 meters per second squared, and multiply it by 100 million, which gives us a figure that exceeds the speed of light. This is accurate because the speed of a black hole is faster than the speed of light. We find out in the movie that Miller's planet is orbiting this black hole and makes one complete rotation every 1.7 hours. If you do the math, you'll find out the planet moves at 99.999999998% the speed of light, which is equivalent to 299,792,457.999 meters per second, according to the movie. In the movie, we are told that 1 hour on Miller's planet is equal to 7 Earth years. Now that we have gathered all of our data, we can verify this information. The standard formula for time dilation is time interval over the square root of 1 minus the observer's velocity squared over the speed of light squared equals the relative time. I'm going to put it right here because that is a lot of things I just said. If we plug the numbers in using the really big number I said earlier, meters per second, as the value for our observer velocity, we'll get a relative time of 44.1 years. This means the movie is incorrect, and it is not equivalent to 7 years. It is 44.1. If the movie did accurately make it so it would equal exactly 7 years on Miller's planet, we would have to be moving at 99.99999867285% of the speed of light, or 299,792,457.9601 meters per second instead of the 99.999999998%, which is 299,792,457.999 meters per second. The difference may seem too tiny to matter, but when working with numbers so large, it can be a grave impact, which has shown how the movie's 7-year estimate is 37.1 years off, despite the observer velocity being less than 0.04 meters per second off. This is because time dilation is, I forget the word. Exponential. That is the word. Thank you. I just want to say before this video ends, this is like 6 hours of numbers that do not make sense in my head. Like, some of these numbers are 18 digits long, and doing the math over and over again, it was something. But hey, that's just a theory. A film theory. Thanks for watching.